Hello guys, welcome to my channel Learning with Sarita. It's my pleasure in presenting a video on the topic electric field due to charged infinite plane sheet. First let us learn what is an infinite plane sheet. A plane sheet is a flat two-dimensional sheet. It has only two dimensions and there is no width. And here we are choosing an infinite plane sheet. What is an infinite plane sheet? The sheet which is of very large in size. That is, we are not able to view the end. It is endless. It is very large in size. That's what we call it as an infinite plane sheet. Now, what is a charged infinite plane sheet? A charged infinite plane sheet is a sheet possessing uniform distribution of positive or negative charges. That is, a charged infinite plane sheet is a sheet possessing uniform distribution of positive or negative charges. And the task of our topic is to find the electric field due to this infinite charged plane sheet. Okay. Which law we are going to use to find the electric field due to this infinite charged plane sheet? We are going to use Gauss law to find the electric field due to infinite charged plane sheet. What is Gauss law statement? The Gauss law states that the electric field or the electric field lines, or we say it as electric flux, which is coming out of a closed surface is equal to 1 by epsilon naught times the charge enclosed. That is, Gauss law states that the electric flux of any closed surface is equal to 1 by epsilon naught times the charge enclosed in the closed surface. Here, for our topic, we have taken an infinite charged plane sheet possessing infinite number of charges. Isn't it? We have taken infinite number of charges. Are we going to consider all the charges to find the electric field? No, we are going to consider the charges that are enclosed in unit area only. Okay. Here in an infinite plane sheet, there are infinite number of charges. And we are not going to consider all the number of charges, all the infinite charges to find the electric field. We are going to choose the charges that are accumulated in unit area only. How we are going to consider this? In our infinite plane sheet, I am going to consider a unit area. There will be some charges accumulated in unit area, isn't it? There is uniform distribution of charges. When I consider unit area, some charges will be accumulated in unit area. So the charges that are accumulated in unit area gives the surface charge density. Okay. Surface charge density, we represent it by sigma. That is, surface charge density is the charges that are enclosed in unit area. Or I can say sigma is equal to Q enclosed per unit area. Okay, now you see here I have an infinite plane sheet with uniform distribution of positive charges. Here I have taken an unit area. That means its length is 1 meter and here also 1 meter. So this is an unit area region. There are some charges accumulated in unit area, isn't it? Now I take a same unit area in some other region of this infinite plane sheet. Here you see, here is also same accumulation of charges. So wherever I consider unit area, there will be same accumulation of charges since the charges are uniformly distributed. Okay, and here these charges, okay, the accumulation of charges, the charges which are enclosed, charges enclosed in unit area gives the surface charge density sigma. Okay, here also the surface charge density is the charges that are enclosed in unit area. And here you see I have increased the area. So as the area is increased, the charge accumulation is also increased. If I increase the area, charge accumulation is also increased uniformly. Now I can say that this infinite plane sheet is possessing a surface charge density sigma. Next, what we have to do is we have to choose a Gaussian surface which is suitable for this plane sheet. What is a Gaussian surface? A Gaussian surface is an imaginary surface. It must be closed and it should be three-dimensional surface and it must possess the symmetry property. That is, our plane sheet is a two-dimensional sheet and the Gaussian surface is a three-dimensional surface. That is, we are going to choose a three-dimensional Gaussian surface for a two-dimensional plane sheet. For this, I am going to consider a circular region in the plane sheet. Here, this is the infinite plane sheet. And I am going to consider a circular region in this infinite plane sheet. I choose a point P which is at a distance r from the circular region. Now, what will be the shape at the distance r? What will be the shape at the distance r? So, for this, we have to have a knowledge of electric field. We know that electric field has both magnitude and direction. Electric field is a vector quantity. It has both magnitude and direction. And at a distance r, the electric field is uniform. And the direction is perpendicular to the area element. Okay. Here at a distance r, wherever the distance is r, the electric field is uniform. E is uniform. That is, we get a circular shape at the distance r. The shape is circular at r. And to the direction of the field is outward, isn't it? The sheet is possessing positive charges, so the electric field lines will be pointing radially outwards and the electric field lines will be pointing radially outwards. So we imagine a Gaussian surface to be a cylinder, isn't it? So we get a cylindrical Gaussian surface. Here at a distance r, the electric field is uniform and to the direction of the electric field is perpendicular to the area element. This in for front side of the plane sheet, isn't it? So we have got a closed three-dimensional cylinder is three-dimension. So three-dimensional Gaussian surface and it is also imaginary. Whether it is satisfying the symmetry property here? No, isn't it? So to satisfy the symmetry property, we consider the back side of the plane sheet. I am going to choose the same distance r on the back side of the plane sheet and choose a point P dash. Here also I get a circular region at the distance r, and the Gaussian surface will be cylindrical. Okay. Now the cylindrical Gaussian surface is following the symmetry property, and here its length will be 2r, and it has one curved surface and two circular edges. Now the Gaussian surface is of imaginary, closed, three-dimensional, and it is possessing the symmetry property, and it is of length 2r, and the surfaces are one curved surface and two circular edges. Here you see the cylindrical Gaussian surface. Its distance is r in front, and on the back side also its distance is r. So the total length will be 2r. Here the distance r is very small when compared to the size of the plane sheet. We start the derivation from the Gauss law. By Gauss law, electric flux phi E is equal to 1 by epsilon naught times the charge enclosed. That is equal to closed integral E vector dot dA vector. And this closed integral is for one curved surface and two circular edges. Now I will split this closed integral into three integral parts. That is integral over curved surface E vector dot dA vector plus integral over front plane surface E vector dot dA vector plus integral over back plane surface E vector dot dA vector, and this can be written as integral over curved surface E dA cos theta plus integral for front plane surface E dA cos theta and plus integral for back plane surface E dA cos theta, and I will take it as first part, second part and third part, and I will find the values separately for each part. Okay, now for the first one, for the curved surface, here is a infinite plane sheet and the circular region for the curved surface. Here is the curved surface, isn't it? Here the curved surface area, I take a element dA, and the element dA and the electric field E vector are in same, that is they are both parallel to each other. dA and E vector are parallel. Now the area vector dA vector, it is in 90 degree to the area element. So the dA vector and E vector are both perpendicular to each other. dA vector and E vector are perpendicular. Now what will be the value of integral E dA cos theta? Here the theta is the angle between dA vector and E vector and is equal to 90 degree. So we get E dA cos theta is equal to integral E dA cos 90. Here the value will be 0. And so for the integral over curved surface, E dA cos 90 will be equal to 0. Now we go for the second part. And for the second part, we are going to consider the circular region. Okay, here this is the circular region and the electric field E is pointing in this direction, and this is the area element dA, and this dA and E vector, dA and E vector are perpendicular. Now what will be dA vector? It is a 90-degree to dA, isn't it? So dA vector and E vector are parallel. This is dA vector. dA vector and E vector are in same direction. So dA vector and E vector are parallel. Now what will be the angle theta between dA vector and E vector? Angle theta will be equal to 0. Now the integral over front plane surface EDA cos theta will be integral EDA cos 0. We know that cos 0 is 1. So this expression will be integral EDA. Now we move on to the third part. Here I am going to consider the back planes. So here the electric field direction is in the outward direction and the area element is dA. Here also electric field E vector and dA are perpendicular, and the area element vector will be pointing in this direction. So E vector and dA vector are parallel to each other. So angle theta will be 0. Now integral E dA cos theta will be integral E dA cos 0. Cos 0 will be 1 and we get the value to be integral E dA. So for the first part, we got the value to be 0. Here I take this equation to be 1. And for the curved surface, the value which I got to be equation 2. And for the front plane surface, the integral value to be 2. And for the back plane surface, I take it to be 4. This is 3 and this is 4. Okay, now I am going to substitute 2, 3 and 4 in equation 1. Okay, 0 and then plus integral E dA plus integral E dA. We know that field is uniform. Electric field is uniform. So we can take it out the integration. E dA plus E integral dA. Integral of dA is A. So this will be EA plus EA. This is electric flux phi E, isn't it? So phi E is equal to 2EA. And 2 we know that electric flux phi E is equal to what? Surface charge density sigma into area. The charge enclosed, isn't it? The by epsilon naught. Flux phi E is 1 by epsilon naught times the charge enclosed. And charge enclosed is the surface charge density into area. And here I can cancel area and area. So I get 2E is equal to sigma by epsilon naught, or we can say E is equal to sigma by 2 epsilon naught. This is the equation for the electric field, and this expression gives only magnitude. What about the direction? We have to introduce the vector notation. E vector is equal to sigma by 2 epsilon naught into n unit. And this equation represents the direction. Okay, here from this equation, from this expression, what we learn, this electric field is independent of R and it is dependent on surface charge density sigma, isn't it? And here the sigma can be positive and it can also be negative. When it will be positive, if I consider a sheet and if the value of sigma is greater than 0, what does it mean? It is possessing positive charges. The sheet is having positive charges and so the surface charge density is greater than 0. And here the normal to this plane will be pointing outward. Okay, this we call it as n cap. And the electric field lines will be pointing in the outward direction for a sheet possessing positive charges. And we can say that the direction of the electric field is along the direction of the outward normal. And this n cap we call it as outward normal. And the main concept here is the field is perpendicular to the plane and 2 it is along the direction of the outward normal. What is the case if the sigma is negative? What does it mean? Sigma is less than 0 and 2 the sheet is possessing negative charges. In this case, the direction of the normal will be represented as minus n cap. And 2 the field will be pointing in the inward direction. And here in this case we call it as inward normal. And for a sheet possessing positive charges we call it as outward normal. And for a sheet possessing negative charges we call it as an inward normal. And the electric field in both the cases will be perpendicular to the plane possessing charges. Now all these concepts are valid for an infinite plane sheet. Now what happens if the sheet is finite in size? For a finite size, here the formula E vector is equal to sigma by 2 epsilon naught is valid only in the middle region of the sheet, or we can say farther from edges. This formula is true only for the middle region or for the regions farther from the edge, that is almost the middle. Okay, why here there arises this concept? Only this is valid in the middle region or farther from the edges. Why we are saying? Here we know the concept. Distance increases, we know that electric field intensity decreases, isn't it? We have learnt a graph previously, R versus E graph. As the radius distance, the distance R increases, what happens to the intensity of the electric field? It decreases, isn't it? So for the case of a finite plane sheet, if the distance is increasing, there will be variation in electric field intensity. So this is valid only in the middle region of the plane sheet. That is where the distance R is very small. Only in those regions the formula E vector is equal to sigma by 2 epsilon naught will be valid. Okay. Okay guys, I hope you all are clear in the concepts of this topic. After watching the video, just click the like button, share my video and subscribe to my channel and travel with me to get full marks easily. Thank you.